Let's go ahead and look at the solutions to the Unit 3 practice exam for Introduction to Statistics. When you're working through the exam, make sure that you read the directions up above. They're usually in this bold type. A lot of times that's where the actual question is, and the part below just gives information and numbers to help you find the solution. So on this first one, it says compute the test statistic used to test the null hypothesis that P1 equals P2. So right away I noticed something. We have two proportions. And for two proportions, we're not asked for a confidence interval, we're asked for a statistics test. So on your calculator, what you're going to look for, under the test menu, of course, is the two proportion z-test. So if you look back on your calculator, you look under Stat, Tests, and then scroll down, your tests are all listed here, and then we start to go into intervals. And you have two proportions, so it has to be this number 6 right here on my calculator. Your calculator might have something different in terms of the numbers, but this is the two proportion z-test that you'll need. So this is the two prop z-test. Okay, so now that we know our calculator command, let's go ahead and look at our numbers. When we have P1 and P2, down here they don't tell us what P1 and P2 is. They don't tell us if P1 is the G-rated or if it's the R-rated, but usually the way it works is the first one listed is P1 and the second one listed is P2. I want to make sure that you understand if you move the direction of these, if you get them mixed up, that you'll just get the negative value. So let's say our answer here was 1.773. If you did the problem backward, for the P2 and P1 being incorrect, you'd get a negative 1.773. So if that happens, that's just telling you have the directions incorrect. So let's go ahead and get started. First of all, even though they're just asking for a test statistic, I'm going to go ahead and write out all the steps up until the test statistic just for some practice. So HO versus HA, I'm talking about the proportion of, we'll say PG movies that make over $3 million is equal to the proportion of R-rated movies that do. And of course my other option here is the proportions are not equal. Second step, we'd have our level of significance, and in this case that's unknown, and then our third step is our test statistic. So that's what we need to calculate right now, is that test statistic. Well, in order to calculate our test statistic, if we jump into our calculator view here, and again we're going under that two proportion z-test, it looks like we need to know x1, n1, and x2 and n2. Okay, so let's go ahead and look back. For P1, that's my PG movies. I need to know x1 and n1. And for P2, which are my R movies, I need to know x2 and n2. So out of 50 PG rated movies, so right now that's telling me how many PG rated movies I looked at. It says 38% have ticket sales. Well, 38% does not go here. 38% is my count, or sorry, is not my count, but my percentage. X is my count. So in order to find X sub 1 here, what I need to do is I need to take 0.38 times 50. So let's go ahead and open up our calculator. Let's take 0.38 times 50. And again, the 38% was given, and the 50 is what my total is for that portion. So this is 19. So 19 is my value for x1. And again, that's equal to 0.38 times 50. Okay, let's do the same thing for my R-rated movies. Out of the 35 R-rated movies, so N2 is 35, 20% grossed over $3 million. Okay, so 20% doesn't go here because that's a percentage. So I need 20% of 35. So 0.2 times 35, and that's 7. So this value of 7 is equal to 0.2 times 35. So now these are the values that I'm going to plug into my calculator. X1, N1, and x2, n2. And again, if you have these mixed up, if you had the PG movies to be x2 and the R movies to be x1, what would happen is your answer would be the negative of what you're supposed to get. So let's go under Stat, Tests, and this would be the 2 proportion z-test. So again, x1 was 19, n1 was 50, so I can't put in the percentages, I have to put in the counts. x2 was 7, n2 was 35. Okay, so now what we're trying to come up with is whether this is a two-tailed test or not, and it is a two-tailed test. We can see that from our alternative hypothesis right here. So I scroll down and hit calculate, and there's my test statistic, 1.773. So let's go ahead and screenshot this and put that in. And again, just one more time, test statistic, 2 proportion z-test. I have all my data filled out. And then once I have all that data filled out, I can run the test and get my results. Now, not all of this information is needed because for this particular example, they basically just asked for the test statistic. I guess I'll take this whole screenshot. Now if we look at this, this is kind of interesting. They say p hat 1 is 0.38. That comes from that 38%. P hat 2 is 0.2, which comes from this 20%. So the z value is my test statistic. Now they don't ask me for my p-value, but if they did, it would be 0.076. So coming back up here, I can see that my test statistic is 1.773. So A is my solution for number 1. Now you can also use these and calculate things by hand using your formula sheets, but I really think that the calculator is the way to go to run through all those calculations to make sure you don't have any errors. Okay, let's go ahead and look at number 2. Now number 2 has the same test statistic that we're going to use, and then find the p-value using that same step, calculator 2-prop z-test. Now the reason I know that it's a 2-prop z-test is if you notice I have 2-prop, prop stands for proportion, and so that's my only option is either a 2-prop z-test or a 2-prop z-interval. So on my calculator, let's see what color I used up here, I used red. So for my calculator, I'm going to use a 2-prop z-test. Okay, so that's the command I'm going to use here. Now in this particular case, they tell us what P1 is, it's this group right here, and they tell me what P2 is, it's this group right here. So I don't have to worry about getting things in the wrong order. However, do be careful because on your calculator, when you enter these values, the x1 goes first and the n1 goes second. So these are almost upside down. So let's go ahead and enter this information in your calculator. Let's start from scratch. So again, you go second, tests, and we come down here to the 2-prop z-test. And now x1 in this particular case is not 100, it's a smaller one, it's 41 out of 100. And then x2 is 35 out of 140. Now this is a two-tailed test because HO is equal to P2, and what we want to do here is check to see what the alternative hypothesis would be, and the alternative in this case is a two-tailed test. It's not implicitly stated, but we can assume that it's a two-tailed test because we're testing for equality. And then we run through our calculations, and again, let's go ahead and show that one more time. Tests. 2-prop z-test is number 6 on my calculator. And again, those numbers come straight from the information given. And then, once we hit calculate, let's look at our summary values. Now this problem is asking for some other pieces of information. They want the p-value. The last one was the test statistic. This one's asking for the p-value. Okay, so 2.627 is my test statistic. My p-value is right here, 0.009. So this is my p-value. Now if you notice, that's not listed here, but this is the one that rounds to 0.009. So this is only going out to 3 decimal places. If it went out to 4 places, you'd see the 0086. So that's my p-value, that's my solution. So again, relying on our calculators here is really nice. It's going to help us be able to check everything pretty thoroughly. Let's go ahead and look at number 3, where we're going to start creating confidence intervals. So just like on our last problem, it's really important that we read the directions up here first. It says construct the indicated confidence interval for the difference between population proportions P1 minus P2. So this is important. They're giving us some information about the direction of the difference because P2 minus P1 would be different. Assume that the samples are independent and that they have been randomly selected. Now they don't tell us what P1 is, but usually we'll read it as the first information we come across. So to me, this looks like P1 is going to be New York. So P1 is talking about New York. P2 is talking about California. Now we're looking at product recognition in each state. So the information that we need here for the confidence interval is going to be X1 and N1, and then X2 and N2. Now remember, it's important that you define these so we get these in the correct order. Now as we're reading through here, it says of 558 New Yorkers, so that's 558 New Yorkers total, it says 193 knew the product, while 196 out of 614 Californians did. You don't need that fraction bar there. So this is really the information that I need. The only other piece of information I should probably think about is this 99% confidence interval. So we need to know our confidence level is going to be 99%. Okay, so now we're going to jump to our calculators to see which test that we use. So again, I have 2 proportions, but I don't want a test this time. I want an actual interval. So I should use 2 proportion interval. So let's see if we can find that. So for our calculator, 2 proportion interval, I think is what they'll have. Let's go ahead and look it up. So we have stat, tests, and again we're looking for intervals, so we want that 2 and then that int. So 2 proportion, there's 1 proportion. So here's our 2 proportion z interval. So that's the one that we want here. So let's go ahead and put in our data. 193 is my x1, 558 is my n1, 196 is my x1, 614 is my n1. Don't forget to change your level of confidence. It's always in there by default to whatever you use for your last problem, but remember this one's a 99% level of confidence. So we need to change that to 0.99. And we'll go ahead and calculate. Let's get a screenshot of this first. Okay, and then there's our confidence interval. Now, your calculator might show more digits than mine. It seems like mine's rounding everything to 3 places. And if they don't show to the correct number of places, just remember to round correctly. So this is my confidence interval. So this is what I want to try and match up here. So negative 0.044 and 0.098, and that rounds to letter D. This is the closest values here to that confidence interval. So let me write that out. Okay, so these again are pretty straightforward if we can identify the correct test to use, and on this particular one it was the 2-prop Z interval. Okay, let's go ahead and look at number 4. And number 4, we're still going to be talking about using our calculators to look at a confidence interval, but this time we're going to be looking at means instead of the T-prop, or sorry, instead of the 2-prop. Okay, so once again, we've got to make sure that you read the directions up top. It says construct the indicated confidence interval. So right away you know you're using the INT and not a test between the two population means. So we know we have a 2 sample and we know we have an interval. And it looks like to me as we read through here, we don't know sigma, so that means we're using a T interval. So this is a 2 sample T interval. So for our calculator, this is a 2 sample T interval, and let's go ahead and find that right away. Stat, tests, 2 sample. No, this is a a Z interval for my first one, but there's the T interval that I want to use. So 2 sample T interval. Now as we're looking through the 2 sample T interval, I can either list my data in list 1 and list 2, that means if I enter data in my list, or I can enter just the statistics. Now the statistics are what I have here in this case where I'm given the X bar, the S, and the N. But there's one other question I need to worry about here at the bottom. Of course I'll update all of this. This says pooled or not. So the directions that we're going to use for pooled is if the standard deviations are not equal, then I use not pooled. So standard deviations not equal, not pooled. And that information is usually going to be given to you. It's not given right here for the sample standard deviations. Pooled or not pooled refers to the population standard deviations. So this is the correct screen. Let's go ahead and start filling in some values. My X1 is 189.1. My standard deviation of my X's is given here as well for my first group. My treatment group is 38.7. My sample size for the first group or the treatment group is 85. X2 is right over here for the control group is 203.7. And the standard deviation is 39.2. And my sample size for the second group is 75. Confidence level, I don't know if I noted the confidence level. Here it is, 99% confidence. Okay, so again, confidence level is 99%, and that's already listed. Now, my pooled, whether I pooled my standard deviations or not, or if I use my pooled estimate, if there's not given to me that they're equal, I'll have to assume that they're not equal. So this is 2 sample, I'll make my notes over here, T interval. And remember, INT is interval, and I'm going to use no pooling or not pooled. And the reason I'm going to choose this is they don't say anything about sigma 1 and sigma 2, so I'm going to assume that they're not equal. And I would use yes pooled if they told me that the population standard deviations could be considered the same. Okay, so let's go ahead and look at my output here. And let's go ahead and calculate. And then this is my information that's going to come up in my confidence interval, will be right at the top. So a lot of this is just summarizing the data that I already put in. And this is my confidence interval. Now if I would have had these in the wrong order, meaning if I would have put these in backward and I put this in for x2, s2, and n2, and this is x1, x2, and n2, then these numbers would have been just the opposite. It would have been negative 62.7 to positive 91.92. So as we're looking at the one example here that works, let's see if we can come up with it. None of these look like they fit. So let's see if we can figure out what happened. Okay, so I probably botched putting the data in. So 189.1, okay, this looks, oh, here's my mistake right here. N2 is 5, N2 should be 75. So let's go ahead and go back in and fix that up. So I guess the lesson here was be careful about how you enter your data in your calculator. So let's go ahead and go back to Stat, Tests, and again I'm looking for the 2 sample t interval. There it is. And this was my mistake down here at N2. It should have been a sample size of 75. Stick with pooled as no and calculate. Well, let's hope we get some better results that'll match up here. Now it's really important on the show your work portion on the test to not mess up entering your data because you won't have any multiple choice values to compare it against. So let's look at our new confidence interval values to see if they make more sense. And it looks like this negative 30.7 to 1.499 matches right up here. So it looks like letter A is the correct confidence interval. So again, this is given on that top row. You might have to do a little bit of rounding to match these up, but this is my confidence interval. Okay, so let's go ahead and look at number 4 then, as being very careful of entering your data and being very careful of the order as well. Okay, let's go ahead and look at number 5 where we're starting to look at paired data and we're trying to find the test statistic with paired data. Now we know we're looking at paired data because we have an X and a Y here. Now you might think, well, we're looking at regression, but let's go ahead and look at the directions again. It says assume that you have to test the claim that the paired sample data come from a population for which the mean difference is mu sub d equals 0. So my HO is mu sub d equals 0. My alternative hypothesis is mu sub d does not equal 0. Continuing on, it says compute the value of the test statistic. So that's what I'm trying to find is the value of the test statistic here. So what I'm doing is I want to take the difference between the X and the Y, and that's my value for D. Now it doesn't tell me which direction that I should take my difference. It doesn't say to take X minus Y or Y minus X. But remember, if you get the order wrong, what will happen is your test statistic will be negative or positive based on the direction. So the number should still match. It just will be positive or negative. So for this one, what I'm going to do is I'm going to enter my data in L1 and L2 in my calculator. So once I enter my data, what I'm going to use then is just the good old one sample t-test because I'm going to break these down into one data set instead of 2. So let's go ahead and see how that looks using your calculator. So we'd go under Stat, and I'm going to edit my columns of my data. I'll clear out those. And I'm going to use the first 2 columns to enter the data, and then I'll use my third column to write a formula to calculate the differences. Okay, so let's go ahead and enter the data from the first row. So I have 5.9, 7.1, 5.7, 10.2, 3.7, 12, 8.1, and 7. So those are your x values. Let's go ahead and enter our y values under L2, 4.1, 6.8, and another 6.8, 5.5, 4.1, 6.7 and 4.2, and our last one is 5.3. Okay, so let's kind of try and keep track of this. So first of all, these values went into L1. So for my x values, that's L1. For my y values, that was L2. So what we want to do is we want to write a formula for L3 that will take that difference. So let's go ahead and do L1 minus L2. We could just as well take L2 minus L1. Remember, the only thing it's going to do is change the sign of my test statistic. So in our calculator, what we'll do is we'll come up here to L3 in the heading right here, and we're going to put second L1, because I'm writing a formula, minus second L2. And what that does is it takes all those differences and populates this according to the differences. So let's go ahead and pop this into the lecture so we can kind of remember where that data comes from. So this is the differences that we're looking at. Okay, so these are my x values, these are my y values, and this is equal to L1 minus L2. That's kind of hard to read. So this is going to be equal to my stylus quit working just a second. Okay, we got that going again. So that's going to be equal to L1 minus L2. So it's good to keep track of what's in your rows and columns when you're entering your data. Okay, so then next for my calculator step, I no longer have a 2 sample, I just have this 1 sample that I'm going to be using. So these 2 data columns have been combined into one by taking their difference. So for my calculator, what I'll do is I'll go under Stat, Tests. Now I don't know sigma here, so I'm going to be going after my sample standard deviation, which would be my t-distribution. So I'm going to be looking at just the t-test right at the top here. It's no longer a 2 sample, it's been combined, so I'm just going to use a t-test. Now under the t-test, I can enter statistics, or I can tell it to go and look in the columns of my data. So I'll choose data here, and mu naught is equal to 0. That's given right here. Okay, and then list that I want to use is L3. That's second 3 here, because that's where my new data set is. The not equal to case is what I'll go after next for my null and my alternative hypothesis. And then I'll just choose calculate. Let's go ahead and put this in our lecture quick so we can see the steps that we're taking here. And then hit calculate, and then we'll look at our summary values. Now again, I'm just looking for the test statistic, and the test statistic is usually toward the top, and in this case it's t equal, looks like 2.391. So 2.391. And again, that's given right here. This is my test statistic. Now if you had reversed these, and instead of taking L1 minus L2, you did L2 minus L1, your test statistic would have been a negative 2.391. But you can see that they're related here. And so if you get them backwards, you can either redo the formula to come up with the correct test statistic, or just switch the order because you know exactly what's going on there. So you just took your difference, L2 minus L1 instead of L1 minus L2. Okay, let's go and look at number 6. Okay, for number 6, it says determine which plot shows the strongest linear correlation. So this word linear is really important. Now remember, linear correlation would assume some sort of a pattern. Now if I look at these data points, it doesn't really look like I see a straight line through here. It almost looks maybe like a bit of a curve. This one looks like it could have kind of a linear pattern in this direction. This one definitely looks like it has a linear pattern in this direction. Now, which one is the strongest? Well, this is definitely not linear, so that can't be my right answer. This one is fairly linear, and so is this one, but if you notice, the data points are more tightly clustered around this line than this line. This one, they're more spread out, so our correct answer here would be C. So again, it's just a comparison of the shape and then the tightness of the clusters around the line. Number 7, we're also going to be looking at paired data as well. This paired data, though, we're not looking at the differences. Specifically up here in the instructions, it says find the value of the linear correlation coefficient R. So they want us to find R. Now they also tell us that we have 6 randomly selected students. I'm not running a test here. All I'm doing is trying to find the linear correlation coefficient. Now there's not a spot that specifically says find the linear correlation coefficient, so we're going to be using a test to do that, but we're not using the test to test anything. It's just the results give us the linear correlation coefficient in the summary values. So the first thing we need to do is to go ahead and enter our data, and I'm going to use L1 for hours. So I have 5, 10, 4, 6, 5, 10, 4, 6, 10, 9. Okay, and then for score, I'll have 64, 86, 69, 86, 59, and 87. Now one of the important things to remember here is make sure all your points are across from each other. Now I'm going to take this information and then we're going to go ahead and run a test, and in the test results we'll have the correlation coefficient. So here is our summary values. Now just a few quick notes. This was X1, this was L1, and this was L2. So again, this is hours, this was score. Okay, so next thing we're going to do is we're going to go across to stat, tests, and again, there's not one here that says linear correlation. What I'm going to do is I'm going to do a linear regression t-test. Now when I do the linear regression t-test, I'll go ahead and put in L1 and L2 in my columns, because again, L1 was my X, L2 was my Y. My frequency is 1, meaning they both appear once. And then my, basically our test statistic here is the not equal to case. I'm not actually testing anything. What I want to get to is just this calculate button. The calculate button will give me the correlation coefficient. And again, I'm really not actually testing for anything. The correlation coefficient is just given in my summary values. So this is linear regression t-test. And then we'll go ahead and hit calculate, and let's look at our summary values. So this gives me my linear regression t-test. We don't even know what these values are. We never did much with these. But if you scroll down, the important number is given right here, R equal 0.224. So again, you have to scroll down to find that number. Now we have a 0.224 and we have a negative 0.224. So I'm kind of wondering, I'm a little concerned that maybe I have the wrong order. So I have to double check something here. Let's go ahead and go to your calculator again, and let's go to second stat plot. And let's go ahead and turn all of our plots off for my case. You might not need to do this. Second stat plot again. And I just want to look at the first one here. So again, I'm looking for a scatter plot. And once I look at the scatter plot, I'll have a pretty good idea of whether it's a positive or negative relationship. Now your X list is L1 like we have here. Your Y list is L2 here. And I should just be able to go ahead and hit graph now. We might need to go to zoom stat. And here's my scatter plot. It doesn't look very linear to me. So let's see if we can squeeze this in. So when I'm looking at this, it looks like it could go in the positive direction. And it does look like it's a very weak linear correlation if it's correlated at all. So I feel pretty confident that the value that we just came up with for our linear correlation coefficient R is equal to that positive value of 0.224. So that's letter C. And again, you have to be careful about the order that you get things in. Otherwise, you'll end up with a negative 0.224 instead. And you have to be very careful about that. Okay, so it does look linear, very weak, because nothing is tightly clustered along this line. So this is my linear correlation coefficient. Okay, so that's number 7. Now, we didn't have to plot this, but I think plotting it is kind of helpful. It gives us an idea of what the picture is of the graph, and then I can compare that to the values that I have and hopefully come up with the correct solution. Okay, let's go ahead and look at number 8. Okay, so again, it's really important to read these bold directions. It says find the predicted value of y corresponding to the given value of x. Use a significance level of 5%. Okay, so really what's going on here, they're saying we want to use this line for prediction if there is a strong linear correlation. If there's not a strong linear correlation, then what I'll do is I'll just say, okay, my answer is y bar. And we can see that y bar is listed down here in a rounded fashion. So what I need to know first is there a strong linear correlation? And it kind of looks like 0.708 could be. So the first thing I want to do is test for linear correlation. So two things that can happen. One, if there is a linear correlation, if I fail to reject HO, meaning there is some sort of a linear correlation, I'm sorry, I better write out HO and HA first, and that will make more sense. So step 1, HO versus HA. Remember, this is rho equals 0 and rho not equal to 0. So this is no linear correlation. And then our alternative hypothesis says that there is a linear correlation. So if there's no linear correlation, I will use y bar for prediction all the time. So we'll use y bar for prediction. If there is some sort of a linear correlation, then I will use my y hat for prediction. Now my y hat is basically my regression line. And then I'll plug in my value of x that I'm interested in there. So I need to take the test here, run through the test, find out what's going on, then I'll know what value to use for my correlation prediction. Okay, so let's go ahead and run the test. 1, HO versus HA. Rho equals 0, rho not equal to 0. This is no linear correlation. And this is linear correlation. Second step is to go ahead and state the level of significance. And if we scroll up here to the directions, we had a significance level of 0.05. My test statistic is given right here as 0.708, but first we need to find a critical value. Okay, Okay, so for our critical value, what we're going to do is we're going to use our tables, our Pearson correlation coefficient R. Now 0.05 was my sample size. What I need to figure out is what n was. So let's go ahead and look back at our problem. And it looks like to me n was given as 8. So n equal 8 is our other important piece of information. So let's go ahead and look at the 0.05 and n equal 8. And that will be our critical value. Now what ends up happening with our critical value is anything beyond that is going to be rejected, and anything less than that will be failed to reject. So again, I'm looking at my 0.05 here, and n equal 8. So I get 0.707. So my critical value is 0.707. Now, just as a quick rule, I will reject HO if my test statistic, which I'm doing in my next step, and it's the absolute value of my test statistic, is greater than my critical value. And then I'll fail to reject HO if the absolute value of my test statistic is less than my critical value. So that's just a quick reminder. Okay, next we're going to go ahead and look at my test statistic now. I know the test statistic was given in the problem, and it was given as R equal, I believe it was 0.708. So let's go ahead and go up and look at that. 0.708, perfect. So now I'll go ahead and make a decision. And I'll need my R value, and I'll need my test statistic. I'm sorry, that was my test statistic. I need my critical value. And my critical value in this particular case was the 0.707. Now these are really close. I really don't like this, that they're so close. So I look at the absolute value of 0.708, and I say, okay, that's larger than, not by much, 0.707. So what I would do here then is to reject HO. And then for my summary, and when you're taking the test, make sure you write out all these steps. Make sure you label this test statistic, label this decision, label this summary. It makes it easy to follow what you've done, so if you have to go back and find any mistakes or compare anything, you can find the correct step really fast. So if we reject HO, so here's HO, if we reject this and throw it out, basically that means, oh, we have some sort of a linear correlation. So the data suggests there is a linear correlation between the variables and that prediction is appropriate. Now, again, if I would not have found that there was a linear correlation, I could have just gone with the Y bar for prediction and been done with it. Okay, so this tells me again that that linear regression is appropriate. So the whole point of this was to figure out what's going on when x equal 10. So we want to plug 10 into my regression equation. So x equal 10, we want to plug this into y hat equals 55.8 plus 2.79x. Okay, so let's go ahead and do that. Plug that in. So again, I'll have 55.8 plus 2.79 times x equal 10. So I get 83.7 for my prediction. And that's my answer then. So if x is 10, I would predict that my y value then would be 83.7. Now again, if I would have failed to reject and there was no linear correlation, I would have used y bar. So this is a really long problem. Make sure that you read carefully when it comes to the exam to see what they're expecting you to do for that. Okay, let's go ahead and try another one of those. So this is really the exact same setup, and so what I need to go through here, I need to go through and check to see if I have a linear correlation. So my first step is check to see if there is a linear correlation. It kind of looks like there could be here because look at our R value. Our R value is pretty big. So let's go ahead and run through the test. HO versus HA, rho equals 0 versus rho not equal to 0. This is no linear correlation. And there is some linear correlation. It doesn't say whether it's positive or negative or how strong it is. It just says there's some linear correlation. Our level of significance was 0.05, and it's not shown right here, but it's up here in the directions for this set of questions is 0.05. Next thing we have is our critical value. Now our critical value, we're going to use this 0.05, and then we also need to know our sample size. In this case, our sample size is 4. So to find our critical value, we'll use n equal 4 and the fact that alpha equals 0.05. And we'll use our table. So using our table, n equal 4, that's the lowest we can go here, and alpha equal 0.05, we can see that the value that we need to find for my critical value then is at the intersection of those two numbers. It's 0.950. So my critical value is equal to 0.950. So just as a quick review, we'll reject HO if the absolute value of my test statistic, and I guess we should be kind of careful about that. I'll write out the word test statistic. If that is greater than my critical value. We'll fail to reject HO if the absolute value of my test statistic is less than my critical value. Okay, so next thing we'll do is we'll find our test statistic, and that was actually given to us up above. That was given in the problem as R equal 0.942. Now if you had to go through and calculate it, we know how to do that as well from the couple problems up above where we found R. Next we'll make a decision. And we know R is 0.942. We know our critical value is 0.950. So the absolute value of R is going to be less than 0.950. Now because of that, we will fail to reject HO. Now if we look at what that means, if we fail to reject this, this means there's no linear correlation. So for my summary, the data supports the conclusion that there is no linear correlation between the variables. So this means prediction with y hat is not appropriate. So what that means is we have to use y bar. Okay, so if we kind of go back here then, if x equal 10, I'm sorry, if x equal 5.4 is actually what was given, and that again is coming from right here, my y bar is the correct prediction at 12.75. I don't even use this in this case because there's not a strong enough linear correlation. It seems like there would be being 0.9, what did we have here, 0.942, but our test statistic, because the sample size was so small, had to be pretty big compared to the critical value, and it just wasn't big enough. So this would mean I would use y bar equal 12.75 for prediction. And this would be true for any value of x that I was given. Okay, so next we're going to look at number 10, where we're going to be working with some regression. Okay, this problem is pretty straightforward, but as usual we want to make sure we read through the directions at the top. It says use the data to find the equation of the regression line. Round the final values to 3 significant digits if necessary. So we have 10 students in a graduate program that were randomly selected, and their grade point averages were recorded when they entered the program, which is our first column, and when they left the program in their current, sorry, not when they left the program, but their current GPAs, which is right here. So we're going to call this L1 and this one L2. Now, according to graphing this, this would be equal to x on my horizontal axis, this would be equal to y. So we have to be careful about how we enter the data, because we want to make sure that it is going to match up with what we have for our scatter plot. Now, we don't need a scatter plot, but I'm probably going to do one in this particular case just to see what the data looks like. So to get started, let's go ahead and go to our calculator, and we're going to go to Stat, Edit, and we're going to put these 2 columns of data in. And of course we need to make sure that we match those up. So I have 3.5, 3.8, 3.6, 3.6, 3.5. Make sure you don't make any mistakes entering your data. 3.5, 3.9, 4.0, 3.9, 3.5, and 3.7. So over here we have our 3.6, 3.7, 3.9, 3.6, and then 3.9 again, 3.8, 3.7, 3.9, 3.8, and then 4.0 at the very end. Okay, so these match up. Whoops. They don't match up. Double check. 3.8 and then 4.0. Now they match up. If you notice, each one has a pair across from it. For some reason, this is rounding everything to 3 places. So I'm going to try and get rid of that. Let's go ahead and go to Stat Edit again, and this is my data that's entered. Looks a little better without all the zeros. And I want to find my linear regression line. So the steps I'm going to go are Stat, Calc. Now I can either do linear regression AX plus B or A plus BX. It doesn't matter which one I use. I just have to be really careful about how I interpret the data. I'm not even really sure why they give you 2 options there. So I look over here and I see A by itself and then an X over here. So I see it in the form of constant plus coefficient times x. So constant plus coefficient times x looks like it matches this one. So in this case, I'm going to use linear regression a plus bx. We could use this one too, but we have to make sure we interpret it correctly. So x list was L1, you can see from up here. Y list was L2. And I'm going to store the regression equation. You don't actually need to do this if you don't want to. I'm going to graph this. I'm just kind of curious how it's going to look. It's not required for this problem though. And then I'll go to calculate. Let's go ahead and put this into our lecture so we can see the commands that were used. And then let's go ahead and calculate. So this is our screen, and this is the one we have to be really careful about how we interpret everything. Okay, so a plus bx. So a is out by itself out front, b is multiplied by x. So the way that this equation would look then is y hat, because that's our line for estimation, is equal to a is equal to 3.67 plus b 0.031 x. Now let's go ahead and see up here what we have that will match. It looks like our closest here is letter A, so that's our solution. Now again, I would like to look at the scatter plot here just because I'm interested to see what it will look like. So we'll go to second, stat plot, plots on, and what I want to have here is my scatter plot. Now not only will I have my scatter plot, but under y equal, it automatically put in my regression line for me as well. So let's make sure that that stat plot is on. It is on, so let's go ahead and hit graph. I may have to adjust my screen. This is spinning right up here, so it tells me it's not quite ready. So I'm going to go to zoom and then zoom stat. And here's my scatter plot, and here is my regression line. That does not look like a very strong linear regression. I'd be interested to see what the correlation coefficient was here. But that is what we have with our line and our data points. So again, this is just kind of informational, kind of interesting. It's not required. So the equation of this line is y hat equals 3.67 plus 0.031x. So this part's not required. This is what's required as the equation. So that's number 10. Let's go ahead and look at number 11. Now in the sample test, it says that these are short answers, and that's what you're also going to have on your actual exam. So these are nice practice to get you ready for that. Now the important part here is that you show all your steps to receive work or just receive credit. I think these are all worth about 20 points, and so that's pretty important. Okay, so first of all, this says goodness of fit. So right in a way, that makes me think of the chi-squared GOF. So for my calculator, let's go ahead and write that down. I'm going to use the chi-squared goodness of fit, GOF. Okay, so it says in studying the responses to a multiple choice test question, the following sample data were obtained. At the 5% level of significance, test the claim that the responses occur with the same frequency. So we have a multiple choice test, and the options are A, B, C, D, and E. And it looks like to me E was answered more frequently than any other. 12 was answered the least frequency. These are my observations. So these are my observed. What I need to do is to come up with my expected. Now they don't say anything about a percentage of a distribution or anything. So what I think that we have here then is my total. So let's go ahead and total these up. If I add all these together, I get 80. And there's 5 outcomes here, so my expected count would be 1/5 times 80, because they're all equally likely, and 1/5 of 80 is 16. So what we're looking at here then is each of the expected counts is equal to 16. So when I enter my data, I'm going to have L1 is my observed, and L2 is my expected. So for my L1, I'll have 12, 15, 16, 18, and 19. And all of these expected are 16. And so that's how I'm going to enter my data. So as usual, I'll go to my stat, edit. I'll clear both of these. So I'll have 12, 15, 16, 18, 19. And then all of my expected counts would be 16. So this is basically saying if I had a multiple choice test and I had 5 different options for my choices, if I had 80 people that took the test, I'd expect to see about, on average, 16 people answer A, 16 people answer B, etc. when those tests are done. Now after my observed minus expected, let's go ahead and plop this into the lecture as well. I'm going to use my chi-squared test, so stat, test, and then scroll up or down to chi-squared goodness of fit. And then observed is L1, expected is L2, and then my degrees of freedom here are one that I'm going to have to know. In this particular case, degrees of freedom are n-1, so 1, 2, 3, 4, 5. My degrees of freedom here should be 4. Again, that's n-1. Now before I calculate that, let's go ahead and make a note of that. Degrees of freedom equal n-1. Okay, now my next step will be to actually go through the calculation. And it gives us some information that we don't necessarily want or need, but we get our p-value out of here. And we could also use our paper tables to compare it to this test statistic, but I'm really more interested in that p-value. So if we look at that p-value is huge. So if I have to make some sort of a decision here, then I should be able to fail to reject HO. But we have all of our summary values now, so we're going to go through and we're going to test this formally. So 1, HO versus HA. So for my chi-squared goodness of fit test, we're basically saying the observed frequencies match the expected frequencies. Actually, I think that's wrong. Up here they were saying test the claim that the responses occur with the same frequency. So this could be the null hypothesis for a different type of chi-squared goodness of fit test. But for this particular example, they said specifically that the responses occur with the same frequency. So the responses occur with the same frequency. Then an alternative hypothesis would be at least one response frequency is different. So that's HO and HA. Alpha is 0.05 up at the top. That's my step 2. Step 3 is my test statistic. And that's chi-squared equals 1.875. This is my test stat. Step 4 would be my p-value. And that's p is equal to 0.759. And then we'll go ahead and make some sort of a decision. Now the information we need to do a decision here, we need our p-value, and then we also need our level of significance of 0.05. We can see that 0.7959 is greater than 0.05, so basically p is greater than alpha here, so I'll fail to reject HO. So 6 is my summary, and again, when you're doing these problems on the exam, please show all of your work. Okay, so I better find a plug-in and I'll be back. So because we failed to reject HO, when I talk about the summary, and again, I failed to reject this, so that means the responses occur with equal frequency. Now you can see that they differ by a little bit, but it's saying it's not statistically significant enough of a difference. So the data supports the conclusion. That, let's see what it was again, the responses occur with the same frequency. Okay, so that's kind of a long test, but that's basically what we're talking about here for that particular problem. And again, it's important that we come up with that expected count. That's probably the toughest part here. Okay, in our next problem, we're going to be using the chi-square test as well, but not the goodness of fit test like we just did. We're going to be looking at a contingency table. So remember, this one was chi-squared goodness of fit, and that's when we're basically given one row or one column of data depending on how it's set up. And for our next problem, we're actually going to be looking at a chi-squared contingency table. So that's this piece right here. Now if you notice, that's a 2 by 2 table, and because that's a 2 by 2 table, we're going to be just using the chi-square test instead of the chi-square goodness of fit test. This is when we use our matrices. So we're going to want to run through this step by step, starting with HO and kind of running through, but let's go ahead and read the directions first. It says use a chi-square test to test the claim that in the given contingency table the row variable and the column variables are independent. Okay, so that gives us a big hint on how to get started here. So my HO versus HA. So basically we have treatment, which is our top here. So treatment and reaction, headache or no headache, are independent of each other. So the alternative would be that treatment and reaction are dependent. So that's the big difference here. The level of significance is 0.05. So my second step here would be alpha equal 0.05. My third step, I would go ahead and I would find a critical value, and this is where we could use our chi-squared tables. Now another option here would be to use our p-value. So it doesn't really matter which one we use. I'm going to go with the p-value approach on this since it's not asking me specifically for a critical value. So because we're going to use the p-value approach, the first thing I need to do is to find my test statistic and then the p-value. So we grab our calculator here, And because this is a contingency table, I need to make my output look like a contingency table, so I need to use a matrix. So I go second matrix. I'm going to edit my first matrix A, and instead of a 2 by 3, I'm going to use a 2 by 2. So I put in the 2 by 2, and then I just go ahead and edit what's here. So I have 11, and it's going across 11, 7, 73, 91. Now I don't have to do anything with matrix B, because this is my observed matrix, and matrix B will be my expected matrix, and the calculator will find that for us. So that's how we put in our matrix to get started. So I put in my matrix A. Okay, and then I go to stat. Whoops, test. And this is just going to be the chi-squared test, not a chi-squared goodness of fit, but just a chi-squared test. And my observed matrix is A, and this is saying put the expected counts in matrix B. It doesn't mean you already have them there, it just means to put them there. Okay, so that's my next step. Then we'll go ahead and hit calculate, and this is my output. I have a chi-squared value, which is my test statistic, and I have a p-value, and then it also tells me what my degrees of freedom are. Now again, I'm going to use the p-value approach on this, not using the critical value or the traditional test for hypothesis testing, or the traditional method. I just need this p-value, and that helps me find everything. And then of course my test statistic. So my test statistic I just found up above was chi-squared equal 1.798. Now again, if you want to use the paper formula sheets, or sorry, the paper test for the chi-squared, you can do that. Number 4 is my p-value, big p-value in this case. P is equal to 0.1799. Next I'll make a decision. So I get P equals 0.1799, and I have alpha equals 0.05. So in this particular case I can see that P is greater than alpha, so I'd failed to reject HO. Then I'll draw some sort of a conclusion, or summary, I guess is what we're used to saying, or a conclusion. So if I fail to reject HO, that means the treatment and reaction are independent of each other. So that means if I have a placebo, that doesn't necessarily mean I'll get a headache or not a headache, or vice versa. I can't use anything to kind of try and guess at what the outcome will be, because they're independent of each other. So that's definitely a 2x2 contingency table. This is specifically the chi-square test. So that's number 12. Let's go ahead and look at 13, which is another contingency table. Whoops. I know this is getting long, but hopefully you guys can just kind of shuffle through until you get to the questions that you have. You don't have to watch the whole thing. I want to make sure I show all my steps, so if you guys get stuck on any problems, you have some specific steps or examples that you can work through. So this is the same type of setup. It says responses to a survey question are broken down according to employment status, and the sample results are given below. 10% level of significance. Test the claim that response, so these are my variables, response and employment status are independent. Okay, so this one for our calculator steps, I'm going to be using my matrix, and I'm going to just be using my chi-squared test. Okay, so let's go ahead and get started by going to second matrix. We'll edit, and this is not a 2 by 2, but it's a 2 by 3 matrix now. So this is going across 30, 15, and 5, 20, 25, and 10. So this is my matrix A. So this is my observed matrix. Okay. Next, after my observed matrix, I'll go to Stat, Tests, and then again, I'm looking for that chi-squared test. And again, observed matrix I just put in as A. My expected matrix will be B. I don't have to do anything to calculate that. It's going to automatically be put into B. And then I can go ahead and run the test. And those are my test statistic, p-values, and degrees of freedom. And I can see right away that that p-value is fairly small. We'll see how it compares when we run our official test. So let's go ahead and run that official test. So step 1, HO versus HA. So if we look back to our other, we have the variables are independent or the variables are dependent. So in this case I have response and employment status are independent. And over here I'd have response and employment status are dependent. Okay, the second step, alpha, was given to us as 0.10. Next thing we have then is our test statistic. I'm going to use the p-value approach here. And our test statistic is equal to 5.94. So right here, this is my test stat. Step 4 is my critical value. Sorry, that's not right. Is my p-value. So in this case, p is equal to 0.0512 or 13, I guess, if we want to round that up. That's my p-value. Next, I'll make a decision. In order to make a decision, I need to know what p is. And I need to know that alpha is 0.10. Okay, so p, 0.0513, is less than 0.10. P is less than alpha, less than or equal to alpha, so then I'll reject HO. So my summary, I think I called it a conclusion last time, we'll call it a summary, is that response, because remember I rejected HO, so I have support for this, response and employment status are dependent. Okay, so let's go ahead and have a look up here again. Response and employment status are dependent. Okay, so it looks like to me, because they are dependent on each other, if I know that you're employed, that's going to influence whether you answer yes, no, or undecided. Okay, so those would be my full steps that I would show if this was on the show your work portion of your exam. Okay, let's go ahead and look at 14. Whoops. Okay, number 14, it looks like we're jumping back into some multiple choice. This kind of has to go back to our analysis of variance or our ANOVA that was at the very end of Unit 3. This is a very easy question. Let's go ahead and read through it. They're asking us just to read these values from the table. It says, given below are the analysis of variance results from a Minitab display. Minitab is a statistical package. Instead of using a calculator, you could use Minitab. Assume that you want to use a 0.05 level of significance, so this is alpha, in testing the null hypothesis that the different samples come from populations with the same mean. So this is the output. So basically each of these is a row. And underneath the row we have all of these values. And it says identify the p-value. Well, the p-value is the one that's under the letter P. So this one's pretty straightforward. Kind of nice for a change. Those other ones are getting pretty long. Now, it doesn't ask us to do anything with the p-value, but that's the p-value. Okay, last problem, number 15. Now this one, we are definitely going to show lots of work because we want to get full credit for those on your exam. And again, each of those show your work problems are worth 20 points. So you want to make sure you show all your steps to get all the complete credit. This one says to test the claim that the samples come from the population with the same mean. Assume that the populations are normally distributed with the same variance. Okay. We have the data below represents the weight losses for people on 3 different exercise programs. So here's exercise A, B, and C. Now the way we're going to do this is we are going to enter this in 3 columns. So this will be L1, L2, and L3. So let's go ahead and enter these and get all of our values, and then we'll go ahead and run the official test. So we will go to Stat, Edit, Clear. Okay, so let's go ahead and enter exercise A and L1. So I'll have 2.5, 8.8, 7.3, 9.8, 5.1, 5.8 and 4.9, 1.1 and 7.8, and 1.2. Oops. Just want 1.2, not 1.23. 4.3, 6.2, 5.8, 8.1, and 7.9. So there's my data. And then once we get my data entered, what we're going to want to do is to go ahead and run the analysis of variance. So let's get our calculator back up here. And so I'd go to Stat, Tests, and then either scroll up or down until you get to ANOVA, Analysis of Variance. Now this one's a little different. I have to put in all the columns I'm using. Now here I'm using 3 columns. Other times you'll be using 4 columns or 5. But I need to put them in individually. So I have L1, comma, L2, comma, and L3. Close parenthesis. And then we just hit enter, but I want to go ahead and copy this in so we can see what the different steps are. And we hit enter. And this is all of my output right here. You can see we can scroll down to get to the rest of the information. But the information that we're really particularly interested in are right up here at the top. So again, lots of other information there, but we really just want the p-value off the top and that test statistic as well. So the first value that we have listed here is the test statistic. The second thing we have listed here is the p-value. Okay, so let's go ahead and run our official hypothesis test, HO versus HA. Let's go ahead and go back up one more time and see what they're asking us to test. At the 1% level of significance, does it appear that a difference exists in the true mean weight loss produced by the 3 exercise programs? So I have exercise program A, B, and C. So I'm saying mu A equals mu B equals mu C. My alternative hypotheses would be at least one differs. So 1 could differ, 2 could differ. It's not saying which one, it's just saying at least one. My level of significance was given up here as well. It is right here at the 1% level of significance. Step 3, my test statistic is given. In this case, it's f equals 1.49. My p-value, and again, when you're doing these, label these and organize them so it's easy to find. 0.2634, we'll call that 0.264. And number 5 would be a decision. So to find our decision, basically what we have here is 0.264 is greater than 0.01. P is greater than 0.01. So that means we should fail to reject HO. So for our summary then, we have information that's basically saying the data supports the conclusion. That, and then I always go back to the problem to see what it supports. The data supports the conclusion that the average weight loss is the same for all 3 exercise programs. Okay, so again, when we're looking at these, a nice little graph is helpful sometimes. Now this is all the further we need to go with this problem, but I'm just kind of curious what the graphs will look like a box plot. So even though it's not required, let's do a quick box plot just to see what these look like. So second stat plot, and I'm going to turn each of these box plots on. And of course my X list is all I'll need for a box plot will be L1. Then I'll go to second stat plot, go to my second stat plot and turn it on. And I'm going to go down to my box plot and I'm going to use X list as L2 on this one. And then I'm going to turn on my third. And I'm going to have my box plot there. This would be second L3. And I'm going to hit graph, and I probably have to reorganize this a little bit. And I think I'll probably have to go into Y equal and clear that out as well. So I'm going to go zoom, zoom stat, and see how all these overlap. And this is the median in the middle. But because these all overlap so much, my true mean probably overlaps as well. So that's why they're saying all 3 means are equal. Okay, now if I had a box plot that was really significantly not overlapping compared to the others, that might be evidence for the alternative hypothesis. So that's just a quick little look at this. Now everywhere else we've made a note about calculators. So for my calculator here, I'm going to use ANOVA. Now notice for most of this test, this practice test, this very long practice test, I didn't really pull any formulas off of the formula sheet. I just was really sure about which test I was using on my calculator to help me out. As usual, if you have any questions, please stop by my office. You can't really bring your questions to class since this is the final, but if you do have questions, let me know. I'm happy to help. You can email me. You can also stop at the Math Center and they're happy to help as well. Good luck on your test.